Imagine being able to see the invisible in the cosmos. What if I told you that right at this moment, mysterious signals from deep space are passing through your body? Welcome to the fascinating world of radio astronomy, where radio waves reveal a universe that our eyes could never see. In today's journey through the cosmos, we'll explore one of astronomy's most revolutionary fields, radio astronomy. We'll discover how this incredible branch of science allows us to peer through cosmic dust clouds, detect mysterious pulsars, and even listen to the echoes of the Big Bang itself. From massive antenna arrays in remote deserts to cutting-edge technology that processes signals from the far reaches of space, we'll uncover how astronomers are using radio waves to revolutionize our understanding of the universe. The story of radio astronomy began almost by accident in 1933, when an engineer named Carl Jansky was investigating static interference in transatlantic telephone communications. What he discovered instead would change astronomy forever: mysterious radio signals coming from the center of our Milky Way galaxy. This accidental discovery opened up an entirely new window to observe the cosmos, leading to some of the most significant astronomical discoveries of the 20th century. Today, radio astronomy has evolved into a sophisticated field that has revealed phenomena we never knew existed, from rapidly spinning neutron stars to enormous clouds of organic molecules floating in space, and even the afterglow of the Big Bang itself. These discoveries have not only transformed our understanding of the universe, but have also led to technological advances that we use in our daily lives, from Wi-Fi to mobile communications. Before we dive deeper into this fascinating journey through the invisible cosmos, make sure to subscribe to Exploring the Universe and hit that notification bell. You won't want to miss our upcoming episodes, where we'll be exploring more mind-bending aspects of our universe. Now, let's begin our exploration of how astronomers are listening to the symphony of the stars. When we look up at the night sky, we're seeing just a tiny fraction of what the universe has to offer. Visible light, what our eyes can detect, is merely a small slice of what astronomers call the electromagnetic spectrum. Radio waves are part of this same family of radiation, but they have much longer wavelengths than visible light, ranging from about the size of a butterfly to longer than a football field. Think of the electromagnetic spectrum as nature's cosmic broadcasting system. Just as your radio can pick up different stations on different frequencies, the universe broadcasts information across a vast range of wavelengths. Radio waves are particularly fascinating because they can travel through cosmic dust and gas clouds that would completely block visible light. This means they can bring us information from parts of the universe that would otherwise remain hidden. But why are these invisible waves so crucial for astronomy? Imagine trying to understand a symphony by only hearing one note, or trying to read a book with most of its pages sealed shut. That's essentially what we'd be doing if we only studied the universe through visible light. Many cosmic objects and phenomena are primarily or exclusively radio loud. Black holes, for instance, can create powerful jets that emit strongly in radio waves. Pulsars, those incredibly dense spinning stellar remnants, beam out radio pulses with clock-like precision. Even the cold hydrogen gas that fills the space between galaxies can only be detected through its radio emission. The universe speaks to us through radio waves in remarkable ways. When massive stars collapse, when galaxies collide, or when matter spirals into supermassive black holes, these events generate distinctive radio signatures. These cosmic radio sources aren't producing sound waves like our everyday radio stations. Instead, they're emitting electromagnetic radiation that carries information about their temperature, composition, motion, and magnetic fields. Some of the most fascinating radio emissions come from molecules tumbling through space. In the cold depths between stars, complex molecules rotate and vibrate, each producing its own unique radio signature. This has allowed astronomers to discover organic molecules, including some of the building blocks of life in the depths of space. It's like each molecule has its own radio fingerprint, telling us about the chemistry of the cosmos. What makes radio astronomy particularly powerful is its ability to see through the cosmic fog. Our galaxy, and indeed the entire universe, is filled with dust and gas that acts like a cosmic smokescreen, blocking visible light from reaching us. Radio waves, however, pass right through this material, allowing us to study regions that would otherwise remain forever hidden, like the center of our galaxy, or the earliest epochs of the universe's history. The universe's radio emissions also tell us about some of its most energetic and violent processes. When galaxy clusters, the largest known structures in the universe, collide, they generate vast radio halos that can span millions of light years. These radio emissions reveal the presence of enormous magnetic fields and high-energy particles, helping us understand how the largest cosmic structures form and evolve. Perhaps most remarkably, radio waves bring us messages from the very dawn of time. The cosmic microwave background radiation, a faint radio glow permeating all of space, is literally the afterglow of the Big Bang itself. By studying these ancient radio waves, astronomers have been able to determine the age, composition, and shape of our universe with unprecedented precision. Through radio astronomy, we've learned that the universe is far more dynamic and varied than our eyes alone would suggest. Every radio observation adds another layer to our understanding, revealing a cosmos that's not silent at all, but constantly broadcasting information across the electromagnetic spectrum, waiting for us to tune in and decode its messages. The birth of radio astronomy reads like a detective story, beginning with an unexpected discovery that would forever change our view of the cosmos. In 1933, a young engineer named Carl Jansky was working at Bell Telephone Laboratories, investigating a peculiar static that was interfering with transatlantic radio communications. Using a rotating antenna, affectionately nicknamed Jansky's merry-go-round, he methodically tracked the source of this mysterious interference. What Jansky discovered was far more significant than simple telephone static. He noticed that the strongest radio signals appeared to come from the same spot in the sky every day, but 4 minutes earlier each day, exactly matching the period of Earth's rotation relative to the stars. This was the smoking gun. The static wasn't coming from Earth at all, but from the center of our Milky Way galaxy. Jansky had accidentally discovered that celestial objects could emit radio waves, effectively opening a new window to the universe. Despite this groundbreaking discovery, the astronomical community initially showed little interest. Enter Grote Reber, an amateur astronomer who would become the world's first dedicated radio astronomer. In 1937, using his own resources and working in his spare time, Reber built the world's first dedicated radio telescope in his backyard in Wheaton, Illinois. His homemade instrument looked like a giant satellite dish, a 31-foot parabolic reflector that he could point at different parts of the sky. Reber's dedication was remarkable. He spent countless nights mapping the radio sky, often working after his day job as an engineer. His persistence paid off when he produced the first radio map of the Milky Way, published in 1944. This achievement demonstrated that radio astronomy could reveal entirely new aspects of the universe, inspiring others to enter the field. The evolution of radio telescopes since these pioneering days has been nothing short of revolutionary. The post-World War II era saw rapid advancement, largely thanks to radar technology developed during the war. Scientists realized that radar equipment could be repurposed for astronomical observations. The Jodrell Bank Observatory in England, established in 1945, converted a military radar antenna into one of the world's first large radio telescopes. By the 1960s, radio astronomy had matured into a sophisticated science. The technique of interferometry was developed, allowing multiple telescopes to work together as if they were one giant instrument. This led to the creation of remarkable facilities like the Very Large Array in New Mexico, which combines 27 individual antennas spread across the desert to achieve unprecedented resolution. The advancement of computing technology in recent decades has transformed radio astronomy yet again. Modern radio telescopes can process enormous amounts of data, allowing them to detect incredibly faint signals from the far reaches of the universe. The Atacama Large Millimeter-Submillimeter Array, ALMA in Chile, completed in 2013, represents the current state of the art, capable of studying everything from planet formation to the birth of the earliest galaxies. Looking to the future, radio astronomy continues to push boundaries. The square-kilometre array, currently under construction across Australia and South Africa, will be the world's largest radio telescope when completed. It will combine thousands of antennas across 2 continents, creating a collecting area of 1 square kilometre. This massive project promises to revolutionize our understanding of the universe once again, potentially even helping in the search for extraterrestrial intelligence. From Jansky's rotating antenna to today's sophisticated arrays, the evolution of radio astronomy represents one of humanity's greatest scientific achievements. What began as an accidental discovery has grown into a field that continues to reveal new wonders about our cosmos, reminding us that some of the most significant scientific breakthroughs come from unexpected places and persistent curiosity. The story of radio astronomy is a testament to human ingenuity and determination, showing how a combination of professional and amateur efforts, technological innovation, and international cooperation can open up entirely new ways of understanding our universe. Each generation of instruments has brought new discoveries, and as we look to the future, radio astronomy promises to continue unveiling the secrets of the cosmos that remain hidden to our eyes. Let's dive into the fascinating world of radio telescopes and discover how these remarkable instruments allow us to listen to the cosmos. At first glance, a radio telescope might look like a giant satellite dish, but it's actually an incredibly sophisticated piece of scientific equipment that works quite differently from the telescopes you might use to stargaze in your backyard. At its most basic level, a radio telescope consists of 3 main components: the antenna, the receiver, and the data processing system. The antenna, often called the dish, works like a giant cosmic ear, collecting radio waves from space. These dishes are typically parabolic in shape. Imagine a huge curved bowl, which helps focus the incoming radio waves to a single point, just like a curved mirror focuses light. At this focal point sits the receiver, a highly sensitive instrument that converts these radio waves into electrical signals that computers can analyze. But what makes radio telescopes so different from their optical cousins? While both types of telescopes collect electromagnetic radiation, they're designed to handle very different wavelengths. Optical telescopes use glass lenses or mirrors to focus visible light, which has wavelengths measured in nanometers. Radio telescopes, on the other hand, need to collect waves that can be several meters long. This is why radio telescopes are so enormous. The longer the wavelength you want to detect, the larger your collecting area needs to be. Another fascinating difference is that radio telescopes can operate 24 hours a day in virtually any weather condition. Unlike optical telescopes, which need clear, dark skies to function, radio waves pass right through clouds, and sunlight doesn't interfere with observations. This means radio astronomers can continue their research even during daylight hours or on cloudy nights. The way we process radio telescope data is also unique. When you look through an optical telescope, you see an actual image of celestial objects. But radio telescopes don't create images directly. Instead, they collect radio signals that must be processed by computers and converted into visual representations that astronomers can interpret. It's similar to how your radio at home converts radio waves into sound, except these cosmic radio waves tell us about the temperature, composition, and motion of objects millions or even billions of light years away. Modern radio telescopes often work together in arrays, combining signals from multiple antennas to create what's effectively one enormous telescope. This technique, called interferometry, allows astronomers to achieve incredible resolution, equivalent to reading a newspaper headline from hundreds of miles away. Now, here's something to think about. Why do you think radio telescopes are often built in remote locations, far from cities and towns? Take a moment to consider this and share your thoughts in the comments below. Could it be related to the same reason you might have trouble getting clear reception on your car radio in certain areas? Before we continue exploring more about radio telescopes, don't forget to hit the subscribe button and turn on notifications. In our next video, we'll be taking a virtual tour of some of the world's largest radio observatories and showing you exactly what happens inside their control rooms. You won't want to miss it. The processing of radio signals requires incredibly sensitive equipment. The signals we receive from space are incredibly weak, often millions of times weaker than the signals used by our cell phones and Wi-Fi networks. This is why radio telescopes need such sophisticated receivers and why they're typically built in remote locations, far from human-made radio interference. It's like trying to hear a whisper from across the ocean. You need both very sensitive hearing and a very quiet environment. The data collected by radio telescopes can reveal phenomena we could never see with optical telescopes alone. The birth of stars hidden inside dense dust clouds, the rotation of pulsars thousands of light years away, and even the echoes of the Big Bang itself. Each observation adds another piece to our understanding of the cosmic puzzle, helping us unravel the mysteries of our universe one radio wave at a time. Throughout the history of radio astronomy, several groundbreaking discoveries have fundamentally changed our understanding of the universe. Each of these revelations has opened new chapters in our cosmic story, showing us that the universe is far more dynamic and mysterious than we ever imagined. Let's start with one of the most remarkable discoveries, pulsars. In 1967, graduate student Jocelyn Bell and her advisor Anthony Hewish detected an unusual radio signal, a series of pulses arriving with such precise timing that they initially wondered if they'd picked up signals from an alien civilization. What they'd actually found was something equally extraordinary. A pulsar, a rapidly spinning neutron star that beams radio waves into space like a cosmic lighthouse. These incredible objects are the compressed cores of dead stars, packing more mass than our sun into a sphere roughly the size of a city. They spin at mind-boggling speeds, some rotating hundreds of times per second, while maintaining timing so precise they rival our best atomic clocks. Perhaps the most profound discovery in radio astronomy came in 1964, when Arno Penzias and Robert Wilson stumbled upon a mysterious radio hiss that seemed to come from every direction in space. This turned out to be the cosmic microwave background radiation, the afterglow of the Big Bang itself. This discovery provided the first direct evidence that our universe had a beginning, a hot, dense state from which everything we see today emerged. This faint radio signal, now cooled to just a few degrees above absolute zero, is literally the echo of creation, giving us a picture of the universe when it was just 380,000 years old. Radio astronomy has also revealed that space is far from empty. In the cold depths between stars, radio telescopes have detected a rich variety of organic molecules, including some of the basic building blocks of life. These discoveries have revolutionized our understanding of astrochemistry and raised intriguing questions about the origins of life in the universe. Complex organic molecules like ethanol, amino acids, and even sugar-related compounds have been found floating in space, suggesting that the ingredients for life might be more common in the universe than we once thought. The study of quasars and black holes has been another triumph of radio astronomy. In the 1960s, radio astronomers discovered mysterious objects that appeared star-like but emitted enormous amounts of radio energy. These quasi-stellar radio sources, or quasars, turned out to be powered by supermassive black holes at the centers of distant galaxies. Through radio observations, we've learned that these cosmic monsters can shoot out jets of material at nearly the speed of light, creating vast radio-emitting lobes that can span millions of light years. The discovery of fast radio bursts represents one of radio astronomy's most recent mysteries. These intense, millisecond-long bursts of radio waves appear to come from distant galaxies, but their exact cause remains unknown. Some FRBs have been found to repeat, while others are one-time events, suggesting there might be multiple types of cosmic phenomena creating these powerful radio flashes. Radio observations have also revolutionized our understanding of galaxy formation and evolution. Through radio surveys, astronomers have mapped vast filaments of hydrogen gas connecting galaxies, revealing the cosmic web that forms the large-scale structure of the universe. These observations show us how galaxies grow, interact, and evolve over cosmic time. Another crucial discovery has been the detection of rotating molecular disks around young stars, providing direct evidence of how planetary systems form. Radio telescopes can peer through the thick clouds of dust that hide these nascent solar systems from optical telescopes, allowing us to witness the birth of new worlds. These discoveries have not only expanded our knowledge of the cosmos, but have also led to practical applications on Earth. The same techniques developed to process weak radio signals from space have found uses in medical imaging, wireless communications, and other technologies we use daily. Each of these discoveries represents a milestone in our understanding of the universe, and each has raised new questions for future generations of astronomers to explore. As radio telescope technology continues to advance, we stand on the brink of even more revolutionary discoveries, ready to unlock more secrets of our cosmic environment. Among the most remarkable scientific instruments ever built, modern radio observatories stand as testament to human ingenuity and our quest to understand the cosmos. Let's explore three of the most significant radio telescope facilities that have revolutionized our view of the universe. The Very Large Array, or VLA, located in the high desert plains of New Mexico, is perhaps the world's most recognizable radio telescope facility. Picture 27 identical antennas, each as tall as a 10-story building and weighing 230 tons, arranged across the desert in a distinctive Y-shaped pattern. These massive dishes can be moved along railroad tracks to change their configuration, spanning distances from less than a mile to up to 22 miles across. This flexibility allows astronomers to adjust the telescope's resolution like adjusting the focus on a camera. What makes the VLA particularly special is its ability to work as one unified telescope through a technique called interferometry. These 27 antennas combine their data to achieve the resolution equivalent to a single telescope 22 miles in diameter. The VLA has been instrumental in numerous groundbreaking discoveries, from studying the aftermath of stellar explosions to mapping the distribution of hydrogen gas in nearby galaxies. Recently upgraded to the Very Long Baseline Array, it can now work in concert with other telescopes across the globe to achieve even higher resolution. High in the Chilean Andes, at an altitude of 16,400 feet, sits one of humanity's most ambitious scientific projects, the Atacama Large Millimeter-Submillimeter Array. This international facility consists of 66 high-precision antennas working together to study some of the coldest and most distant objects in the universe. The site's extreme altitude and aridity make it ideal for detecting millimeter and sub-millimeter wavelength radiation, which is easily absorbed by water vapor in Earth's atmosphere. ALMA's capabilities are extraordinary. It can detect the faint radio signals from molecules in space with unprecedented sensitivity, allowing astronomers to study the chemical composition of distant galaxies and watch planets forming around young stars. The facility is so sensitive it could detect a birthday candle on the moon. The antennas can be spread across the high-altitude plateau to distances up to 16 kilometers, providing incredible detail in its observations. But perhaps the most ambitious radio astronomy project yet conceived is the Square Kilometer Array, currently under construction across 2 continents. When completed, it will be the world's largest radio telescope, with a total collecting area of 1 square kilometer. The project is split between 2 main sites, SKA Low in Western Australia, focusing on lower frequencies, and SKA Mid in South Africa's Karoo region, designed for medium frequencies. The scale of the SKA is mind-boggling. It will use thousands of dishes and up to 1 million low-frequency antennas, working together as one enormous virtual telescope. The data processing requirements are equally impressive. The SKA will generate more data traffic than the entire internet, requiring supercomputers capable of performing calculations at a rate of over 100 petaflops. That's 100 million billion calculations per second. The SKA's scientific goals are equally ambitious. It will be able to detect extremely faint radio signals from the early universe, potentially revealing how the first stars and galaxies formed. It could help us understand the nature of dark energy, test Einstein's theory of relativity in extreme conditions, and even search for signs of extraterrestrial technology. The telescope will be so sensitive, it could theoretically detect airport radar signals from planets orbiting other stars. What makes these facilities particularly remarkable is their international nature. They represent collaboration between dozens of countries, thousands of scientists, and countless engineers and technicians. The management of these facilities requires careful coordination of resources, scheduling of observations, and processing of enormous amounts of data. Each of these facilities also faces unique challenges. The VLA must contend with maintenance of its railway system and the harsh New Mexico climate. ALMA's high-altitude location makes maintenance challenging and requires special consideration for the health and safety of its staff. The SKA must overcome the challenges of coordinating observations across 2 continents while processing unprecedented amounts of data. These magnificent facilities represent not just technological achievement, but human ambition and cooperation on a global scale. They continue to push the boundaries of our understanding of the universe, promising new discoveries that will reshape our understanding of the cosmos for generations to come. Let's dive into some captivating facts about radio astronomy, starting with the world's largest single-dish radio telescope, the 500-meter Aperture Spherical Telescope, or FAST, located in China's Guizhou province, is truly an engineering marvel. Imagine a dish larger than 30 football fields, nestled within a natural depression in the mountains. Its surface is made up of 4,450 individual panels that can be adjusted to focus on different parts of the sky. The telescope is so sensitive that a cell phone on the moon would be detectable to its receivers. To maintain radio silence, a zone of over 3 miles around the telescope was cleared, and more than 9,000 people were relocated to create this scientific sanctuary. The processing of radio signals from space is a fascinating technological achievement in itself. When radio waves from distant cosmic objects reach our telescopes, they're incredibly weak, often billions of times fainter than the radio waves we use for communication on Earth. These signals first hit the telescope's dish, which focuses them onto highly sensitive receivers cooled to near absolute zero temperatures. These receivers convert the radio waves into electrical signals, which are then amplified and digitized, but the real magic happens in the processing centers. Modern radio telescopes generate enormous amounts of data, often several petabytes per day, equivalent to millions of hours of HD video. This data undergoes complex processing using supercomputers that perform trillions of calculations per second. These computers filter out interference from human-made radio sources, combine signals from multiple telescopes, and transform the raw data into images and spectra that astronomers can analyze. It's like trying to hear a whisper from across the galaxy while filtering out the noise of a rock concert. The search for extraterrestrial intelligence represents one of radio astronomy's most intriguing applications. Since 1960, when Frank Drake conducted the first modern SETI search, Project Ozma, radio astronomers have been scanning the sky for signs of artificial signals that might indicate intelligent life elsewhere in the universe. The rationale is simple but compelling. Radio waves can travel vast distances through space with relatively little degradation, making them an ideal medium for interstellar communication. SETI projects have grown increasingly sophisticated over the years. Modern searches can monitor millions of frequency channels simultaneously, looking for patterns that might indicate artificial origin. The Breakthrough Listen initiative, launched in 2015, represents the most comprehensive SETI effort to date, using some of the world's most powerful telescopes to survey the million stars closest to Earth and the center of our galaxy. Some of the most fascinating aspects of SETI involve the questions of what to look for and where to look. Scientists have identified certain frequencies as particularly promising for interstellar communication, such as the water hole, a quiet region of the radio spectrum between the emission frequencies of hydrogen and hydroxyl, the components of water. Some researchers suggest that any technologically advanced civilization would recognize this frequency range as ideal for communication. Another fascinating aspect is how radio telescopes deal with interference from Earth. Radio astronomers have developed incredible techniques to distinguish between artificial and natural signals. For instance, natural radio sources typically produce signals that spread across a range of frequencies, while artificial signals tend to be concentrated in narrow frequency bands. Additionally, due to Earth's rotation, signals from space show a characteristic drift in frequency known as the Doppler shift, which helps distinguish them from local interference. The future of radio signal processing looks even more exciting. Machine learning algorithms are being developed to help identify unusual patterns in the vast amounts of data collected by radio telescopes. These AI systems might be able to spot patterns that human observers would miss, potentially leading to new discoveries or even the detection of signals from other civilizations. The impact of these technologies extends beyond astronomy. The same techniques developed to process weak radio signals from space have found applications in medical imaging, wireless communications, and data processing. The need to handle enormous amounts of radio telescope data has driven innovations in computing and data storage that benefit many other fields. From the largest single structures humans have ever built to the search for alien intelligence, from processing some of the weakest signals ever detected to handling some of the largest data flows ever created, radio astronomy continues to push the boundaries of human knowledge and technological capability. Each new advance brings us closer to understanding our cosmic environment and perhaps to answering one of humanity's oldest questions. Are we alone in the universe? Radio astronomy stands at an exciting crossroads, with leading experts sharing their insights about current developments and future possibilities. Let's explore what some of the field's most prominent voices have to say about where radio astronomy is headed. Dr. Jocelyn Bell Burnell, the pioneering astronomer who discovered pulsars, reflects on the field's evolution. Radio astronomy has transformed our understanding of the universe in ways we couldn't have imagined 50 years ago. The instruments we have today would have seemed like science fiction when I first started observing. She emphasizes how modern technology has revolutionized the field. What once took weeks of observation and analysis can now be done in real time, allowing us to catch transient events as they happen. Current research is pushing boundaries in multiple directions. Dr. Sarah Burke-Spolaor, a leading researcher in fast radio bursts, FRBs, shares her perspective. We're just beginning to understand these mysterious bursts of radio energy. Every new discovery seems to raise more questions than answers, but that's what makes this field so exciting. The next decade will likely reveal multiple populations of FRBs with different origins. Several cutting-edge research projects are currently underway. Dr. Catherine Bouman, known for her work in black hole imaging, discusses how radio astronomy is entering a new era. We're not just collecting more data, we're developing new ways to process and understand it. Machine learning and artificial intelligence are becoming essential tools in our field, helping us identify patterns that human observers might miss. The search for extraterrestrial intelligence remains a fascinating aspect of radio astronomy. Dr. Andrew Siemion, director of the Berkeley SETI Research Center, explains, "We're now able to survey more of the sky across more frequencies than ever before." The breakthrough, LISTEN initiative, is generating more data in a day than previous SETI projects collected in a year. We're also getting better at distinguishing artificial signals from natural phenomena. Looking toward the future, Dr. Philip Diamond, Director General of the Square Kilometre Array Organization, shares his vision. The SKA will revolutionize our understanding of the universe. We'll be able to track the evolution of galaxies, test Einstein's theories in extreme conditions, and possibly detect signs of life on exoplanets. The amount of data we'll collect is staggering, equivalent to the entire world's internet traffic. Current research priorities are diverse and ambitious. Dr. Nadia Zakamska of Johns Hopkins University discusses her work on galaxy evolution. Radio observations are revealing how supermassive black holes influence their host galaxies. We're seeing evidence of massive outflows that can halt star formation across entire galaxies. This is changing our understanding of how galaxies evolve. The future of radio astronomy appears increasingly international and collaborative. Dr. Fernando Camilo, Chief Scientist at the South African Radio Astronomy Observatory, notes, "We're seeing unprecedented cooperation between facilities worldwide." The future of radio astronomy isn't just about building bigger telescopes, it's about connecting existing ones in clever ways to create virtual telescopes the size of our planet. Emerging technologies are opening new possibilities. Dr. Lisa Cooley, Director of the Center for Astrophysics, describes upcoming developments. Quantum sensors and advanced computing will transform our capabilities. We're approaching an era where we can study the earliest galaxies in detail and possibly detect radio signatures of biological processes on exoplanets. Looking even further ahead, Dr. Jason Wright, Professor of Astronomy and Astrophysics at Penn State, speculates about future discoveries. Within the next 2 decades, we might detect technosignatures from other civilizations, map the cosmic web in unprecedented detail, or discover entirely new classes of astronomical objects. The history of radio astronomy shows us that the most significant discoveries often come as complete surprises. These expert perspectives paint a picture of a field that continues to evolve rapidly, driven by technological innovation and human curiosity. As radio astronomy enters its next chapter, it promises to reveal more about our cosmic environment and our place within it than ever before. What cosmic objects can only be detected through radio telescopes? Before you share your thoughts in the comments section, consider that vast portions of our universe remain completely invisible to our eyes, yet broadcast powerful radio signals across space. Think about what might be hiding in the darkness between the stars, waiting to be discovered. While pondering this cosmic question, it's fascinating to realize how radio astronomy has revolutionized our daily lives. The technology developed for peering into the depths of space has found its way into our homes, phones, and everyday devices in ways most people never imagine. Take Wi-Fi, for example. The technology that lets you stream videos and browse social media owes a significant debt to radio astronomy. The complex algorithms developed to clean up weak radio signals from space were adapted to help wireless networks function more efficiently. When you're using your smartphone to video chat with friends, you're benefiting from decades of radio astronomy research into signal processing and data compression. The impact extends far beyond communications. Medical imaging, particularly MRI technology, employs techniques first developed by radio astronomers to convert radio signals into clear images. The same mathematical processes used to piece together images of distant galaxies from multiple radio telescopes now help doctors create detailed images of our bodies. It's remarkable to think that the same principles used to study black holes are now saving lives in hospitals worldwide. Modern weather forecasting has also benefited enormously from radio astronomy technology. The sensitive receivers developed to detect faint cosmic signals have been adapted to improve weather radar systems. The next time you check a weather app on your phone, remember that its accuracy partly stems from techniques pioneered by radio astronomers studying cosmic storms on distant planets. GPS technology, which many of us use daily, relies heavily on precise timing and signal processing, areas where radio astronomy has made significant contributions. The ultra-precise atomic clocks used in GPS satellites emerged from astronomy's need for extreme accuracy in measuring cosmic phenomena. When you're using your phone's navigation system, you're essentially using technology developed to study pulsars and distant galaxies. Even our microwave ovens have a connection to radio astronomy. The magnetron, the device that generates microwave radiation in your kitchen, was refined through research into radio waves from space. The frequency used in microwave ovens was chosen partly because it wouldn't interfere with astronomical observations. The telecommunications industry has been perhaps the biggest beneficiary of radio astronomy research. The development of low-noise amplifiers, efficient antenna designs, and advanced signal processing techniques, all crucial for modern cell phones, emerged from the need to detect and analyze incredibly weak signals from space. The next time you make a cell phone call, you're using technology that was first developed to listen to the whispers of distant stars. In the realm of computing, radio astronomy's demands for processing enormous amounts of data have driven innovations in hardware and software design. The techniques developed to handle the massive data flows from radio telescopes have influenced everything from big data analytics to cloud computing. When you're using a streaming service or cloud storage, you're benefiting from solutions originally developed to process astronomical data. The technology transfer goes both ways. Commercial developments in computing and electronics have allowed radio astronomers to build more powerful instruments, creating a virtuous cycle of innovation. This partnership between astronomy and industry continues to drive technological progress in both fields. Looking to the future, radio astronomy continues to push technological boundaries. Research into quantum sensors for telescope receivers is advancing our understanding of quantum computing. Development of more efficient ways to process massive datasets is contributing to artificial intelligence and machine learning technologies. The need to coordinate observations across global networks of telescopes is advancing our knowledge of high-speed data networks. So, as you consider what cosmic objects might only be visible to radio telescopes, remember that the technology developed to study these invisible wonders has transformed our world in very visible ways. From the smartphone in your pocket to the medical imaging that keeps you healthy, radio astronomy's impact extends far beyond the stars. Now, we'd love to hear your thoughts. What kinds of cosmic objects do you think can only be detected by radio telescopes? Share your ideas in the comments below, and let's discuss how these invisible cosmic wonders have led to the technology we use every day. Don't forget to like this video and subscribe to our channel for more fascinating connections between space science and everyday life. As we conclude our journey through the invisible cosmos, let's reflect on the remarkable story of radio astronomy and its profound impact on our understanding of the universe. We've explored how this revolutionary field has unveiled cosmic phenomena that would forever remain hidden from our eyes alone, from the violent births of distant galaxies to the ethereal whispers of the Big Bang itself. Throughout this exploration, we've discovered that the universe is far more dynamic and complex than our visible observations alone would suggest. Radio astronomy has shown us pulsars spinning with incredible precision, vast molecular clouds where new stars are born, and the mysterious dance of supermassive black holes at the hearts of galaxies. It has revealed to us that space is not empty, but filled with complex molecules, including the building blocks of life itself. Perhaps most remarkably, radio astronomy represents humanity's triumph over the limitations of our natural senses. Through ingenuity, persistence, and technological innovation, we've developed the ability to see the invisible and hear the silent cosmic broadcasts that continually pass through our world. From Carl Jansky's first accidental detection of cosmic radio waves to today's massive telescope arrays spanning continents, we've expanded our cosmic awareness far beyond what our ancestors could have imagined. The future of radio astronomy holds even greater promise. As we build more sensitive instruments and develop more sophisticated ways to process the cosmic signals we receive, we stand on the brink of even more extraordinary discoveries. The square-kilometer array and other next-generation facilities will push the boundaries of our knowledge even further, potentially revealing the secrets of dark energy, the nature of gravity, and perhaps even signs of other civilizations among the stars. But beyond the scientific achievements, radio astronomy reminds us of something profound about human nature: our unquenchable curiosity and our ability to overcome seemingly insurmountable challenges through creativity and collaboration. It shows us that the universe has many stories to tell, if only we learn to listen in the right ways. Before we end this cosmic journey, I want to invite you to become part of our growing community of space enthusiasts. If you've enjoyed this exploration of radio astronomy, make sure to subscribe to Exploring the Universe and activate the notification bell. This way, you won't miss any of our upcoming videos, where we'll continue to unravel the mysteries of our cosmos. Share this video with friends who might be fascinated by the invisible universe around us. Every like and share helps us reach more people and spread the wonder of astronomical discovery. Join us in our social media communities, where we share additional content, behind-the-scenes looks at astronomy, and updates on the latest cosmic discoveries. Remember, every time you look up at the night sky, there's an invisible cosmic symphony playing all around you. Radio astronomy has shown us that the universe is far more extraordinary than we ever imagined, and we're only beginning to understand its full complexity. Until our next cosmic adventure, keep exploring, keep questioning, and keep wondering about the magnificent universe we call home.